what is this quantity called Q? We're measuring a transfer function. You see I've got input and output, and with a structural system, which I certainly became familiar with early on in my career, and this is the first transfer function that I measured, you're certainly putting input into the structure, and that's usually a measured force. Your output is typically measured with an accelerometer, and so your output is an acceleration. This is where we get our A over F, or acceleration over force. We create a bunch of these when we're doing a modal analysis. Acceleration over force transfer function. In the acoustic side of the world, we can do exactly the same thing. Instead of measuring acceleration, we're going to measure the acoustic output of our system, and that would be a pressure, right? We're going to use a microphone. And for our input, we're going to use this thing called Q, or acoustic force, okay? So just like we have an A over F, we can also measure a P over Q. So what is Q? Well, if I have this sound source, and in this case it's a speaker, and I want to understand the acoustic force coming out of this speaker, it's a noise source, I'm going to be trying to quantify or measure Q. Well, we said Q was a volume acceleration. Well, how do I measure volume acceleration? Well, let's break this down a little bit. Think of this as really an area multiplied by an acceleration. So if we take this speaker and we break it down into some sub areas, if you will, and then I measure the acceleration, I measure an acceleration at these dots. So I could put an accelerometer in the center of that speaker cone. And if I was interested in the Q of the speaker cabinet here, I could also measure the acceleration up here. And I have a given area that I can measure that acceleration over. So I have an area and an acceleration. Meters per squared times meter per second squared. That gives me meters cubed per second squared, or a volume acceleration. Okay, so this is how we measure Q in practice. So if I have a surface that is generating noise, and I want to understand where on that surface most of the noise is coming from, or I want to break it down into its different components, I can break that surface down into these smaller areas, and then measure an accelerometer, or measure an acceleration with an accelerometer at the center of each of those patches. So in this picture, I'm looking at like an automotive instrument panel that's broken down into different areas. I could then put an accelerometer in the middle of each of those areas and come up with a Q, an operating Q for this vehicle under some load condition. And I would understand which areas produce the most sound or the most acoustic force. So I divide my area into smaller patches, measure an accelerometer or measure an acceleration in there. And as my frequency range of interest goes up, those patches need to get smaller and smaller. And that's really just due to the wavelength of sound and the physical property of sound at lower frequencies that gets bigger and bigger. And so at higher frequencies, that wavelength gets shorter and shorter. And so we need to use a smaller and smaller area to extend that frequency range. So this is how we measure a Q, kind of an operating or output Q. However, if we have a Q source, like we're talking about today, we can measure some really kind of interesting things. So again, our inputs are forces and acoustic forces, or Q, and our responses are acceleration and sound pressure, or A's and P's, okay? So using these four letters for our two inputs and two outputs, we can come up with four different types of transfer functions, right? A over F, we've talked about that. That's an acceleration per unit force. Real typical impact hammer measurement or a shaker. You could also have an A over Q, right? Where I'm measuring the acceleration on a structure due to an acoustic force. So if you imagine that interaction between a loud sound or a sound source actually sending those sound waves out, causing the structure to shake a little bit, we could then measure that airborne, structure-borne interaction with an A over Q. Also have a P over F, which is a pressure per unit force. Again, this is very common in like a transfer path analysis where I'm trying to, let's say I'm working on an automobile and I want to understand what are the different paths or ways that energy is getting to the driver's ear. So my P is my driver's ear location with a microphone, and then I could essentially bonk on my structure in all these different places and generate a P over F. Similarly, there's also this P over Q where I'm measuring an acoustic response from an acoustic force. So I just want to know the transfer function, fully airborne. A over F, structure-borne transfer function, A over Q, airborne, structure-borne, P over F, airborne, structure-borne, P over Q, simply just airborne. We're going to see that there's a sort of a special relationship between this P over F and the A over Q. We'll take a look at that next. So very common measurement for a transfer path analysis in an automobile we were just talking about. We have this receiver location, this driver's ear, and we want to understand from our engine, let's say our engine or our motor in the case of an electric vehicle, this is our source. We want to know how much engine noise gets to our driver's ear through the engine mounts. So I've got some P, that's my target or my receiver, if you will, is the driver's ear pressure microphone. And we're going to make some impact measurements at the two engine mount locations. So in this case, I've got a simplified vehicle. I've got two engine mounts. So I could remove the engine, remove the mounts, take my impact hammer and hit the structure on the first engine mount bracket with my impact hammer. I'm measuring the F, I'm measuring the P response, and I would measure this thing called a P over F. How much pressure is produced by putting in force at this location. As I have two mount locations, I'm going to have to do a second measurement. So now I'm putting in my force here, and I'm going to measure a different function of P over F, where the F is applied at location 2. Okay, so I've got two locations. I create two P over Fs, right? This will help me understand how energy gets in and flows through my structure and produces noise at the driver's ear, given that the force is acting on my structure at either one of these mount locations. Now, in reality, I don't usually just have two engine mount locations, and I usually don't just care about one direction. I've only talked about the vertical direction here. In reality, it's more likely that I'm going to be measuring 3 transfer functions at each mount location, because I've got a vertical, a lateral, and a fore aft X, Y, and Z component to that force acting on my structure. So even in this simplified case, I've got 2 locations, but 3 directions each. So now I'm measuring 6 FRFs or P over Fs in order to quantify the structure-borne, airborne interaction. So now I'm taking my impact hammer and I'm hitting each location at least 3 times, plus I'm taking a bunch of averages at each of those locations in each of those directions. And so you can see how the measurement time grows very, very quickly. And so we'd be interested in a more efficient way to do this, okay? This is what is called a direct measurement. Putting in a force, I'm measuring a pressure, I'm getting a P over F in the direct way, okay? We can also measure transfer functions reciprocally, okay? Which means instead of putting my force or my energy into the system here and measuring the output at the driver's ear, I would do this the opposite way, as I would put my force in here at the driver's ear and measure my response at my mount locations. Now you see my forces have an X, Y, and Z component. With an impact hammer, I can only hit in one direction at a time. However, if I'm going to do this reciprocally, do we have a transducer that can measure the response in all 3 directions on that structure at once? The answer is yes, and I'll get to that in just a second. But first, I'm going to show you what allows us to do this. And this is sort of a simplified approach, but it does hold true. So if we look at that P over F transfer function, and we look at the units involved in P over F. So pressure is a Newton per meter squared, or Pascal, right? Over a unit of force, which is Newton. We simplify that down, and we end up with 1 over meter squared as our essentially reduced unit for a P over F. If I look at this A over Q function, and I do the same thing, acceleration, meters per second squared on the numerator, and then on the bottom is Q, or meters cubed per second squared, volume acceleration. You simplify those down, and you end up with the same units, 1 over meter squared. Okay, and this allows us to draw equivalency between a P over F and an A over Q. So instead of measuring the direct method and measuring all 6, 9, 12, 81 of these P over Fs in the direct direction, I can do this reciprocally with an A over Q. So now I'm going to be using a Q source as my acoustic force. I'm going to be measuring my response with an accelerometer. There are triaxial accelerometers, and this is where the advantage is really going to pay off for me, is I can measure XYZ with one measurement, putting an accelerometer at my engine mounts, and then up here where my response was, I'm going to put my acoustic force. Because I can use the equivalency between a P over F and an A over Q, I can do all of these measurements in one shot and measure all 6 transfer functions, A over Q's or P over F's equivalent, by doing one measurement. And realistically, I'm still going to be taking averages here. When you're doing transfer function measurements, you're always going to want to take a bunch of averages so that no individual hit or excitation is taken off by itself. You can always have outliers. But the real benefit is I'm getting 6 for every one measurement I do, okay? And this is the real benefit when you have something that can generate a measurable Q, like a Q source. So this is why we are interested in these devices, is that we can play some of these games and get some really interesting measurement.